In this video, we're going to look at how lines interact with each other in 3 dimensions. So let's consider 2 lines in general. We'll consider line 1, which has the vector equation r1 is equal to a1 plus s times b1. And we'll consider line 2, with vector equation r2 equals a2 plus t times b2. These 2 lines can interact with each other in a few different ways. These 2 lines could be parallel to one another. The easiest way to verify that is to check to see if their direction vectors are scalar multiples. So if b1 is equal to some scalar multiple of b2. So for example, consider these 2 lines where r1 is equal to 1, 2, 3 plus s times the vector 1, 1, 1, and the vector r2 is equal to 1, 2, 4 plus t times the vector 3, 3, 3. I can see here their direction vectors are scalar multiples of one another. So what that means is that these lines are going in the same direction. And so within that 3-dimensional space, these lines are running parallel to one another. They will never cross, and they're going in the same direction. Another way that these lines could be interacting is they could be coincident lines. Coincident lines are actually the same line. So coincident means they're coinciding, they're overlapping. So what we're essentially looking at is 2 equations for the same line. And if you recall, last time we talked about how you can have infinitely many equations for lines in 3 dimensions, so this could actually be quite common. You will know that 2 lines are coincident if their direction vectors are scalar multiples, and if one of your position vectors is on both lines. So if you can take that position vector, say from the first vector, and you can discover that it is in fact on both lines, you know that these lines are coincident. So consider the 2 lines seen here. They're given by the equations r1 and r2 again. You can see their direction vectors are scalar multiples because the direction vector from the first line is 1/2 the direction vector from the second. And so now what we would have to check is to see if one of those position vectors, either this one or this one, we have to see if they will also work within the other line. So what I've done here is I've plugged in the position vector for a point on my first line into the vector equation for my second line. So essentially what I'm looking to see here is, will the point 1, 2, 3 occur on both lines? I already know it's on the first line. Now I'm checking to see if it's on the second line. To solve this question, I would need to split up my vector equation into those parametric equations and solve for the parameter in each one. If those parameters match up, then I know this point is in fact on the line. For my x component, I get that the parameter t is equal to 1. The same is true for my y component, and it's also equal to 1 for my z component. So because I get the same value of t for all 3 of those components, I know that that point 1, 2, 3 is on that second line, and if it's on both lines, that means I'm actually looking at the same line. It's going in the same direction, it's passing through the same point, therefore it must be the exact same line. So they are coincident lines. That's 2 equations for the same 3-dimensional line. Another way that these 2 lines could interact is that they might intersect one another, so they may cross at a single point. What this would mean is that the 2 vector equations are actually equal to each other at some point for some value of s and t within the real numbers. So it means if I set the equations equal, I should be able to solve for s and t values and get a concrete result that works for the equations. To show you what that looks like, I've given 2 vector equations for lines here, and we're going to set them equal to each other. So the easiest way to do that is to split them up into their parametric equations again. So focusing specifically on x components, y components, and z components. So reading along through my x components and forming the equations and setting them equal, I find that -5 plus 2s is equal to -4 minus t. For my y components, I get 4 plus s is equal to 9 plus t. And for my z components, I get the equation -5 plus 3x equals 7 plus 2t. Now right now these aren't in the form that I'm going to be working with them in. I'm going to want to simplify these a little bit. I'm going to do that by moving all the variables to one side of the equation and all of the constant terms to the other side of the equation. For my x components, this becomes 2s plus t equals 1. For my y components, the equation becomes s minus t equals 5. And for my z components, the equation becomes 3s minus 2t equals 12. What I have here now are 3 equations with only 2 unknowns. This puts me in a really ideal position because I can actually solve for those values of s and t using substitution or elimination. However, you'll notice I have an uncharacteristic third equation here, which is normally not needed when I'm doing substitution or elimination. We always say to do substitution or elimination, you need 2 equations and 2 unknowns. What's going to happen here is I'm going to be able to solve for s and t using a method of my choice, using 2 of the equations, and I will check those results in the third to ensure that they are consistent. So if I number off these equations as 1, 2, and 3, the strategy I'm going to take here is using elimination with equations 1 and 2. I'm going to add them together to eliminate t. That gives me the equation 3s equals 6, so s is equal to 2. If I take that value and plug it into, say, equation 2, I get 2 minus t equals 5, so t has to be equal to negative 3. So I solve for those 2 values using equations 1 and equations 2. So that means I'm going to need to check them in equation 3. So in my check step here on the left side of the equation, I have 3 times 2 minus 2 times negative 3. So I'm going to evaluate that and get 12, which happens to match the right side. So I know that these values of s and t are correct. Now, of course, it's worth noting I have not actually found the point of intersection by doing this step. I have found that a point of intersection exists. If I actually want to find the coordinates of that point, I would have to plug in my parameters into one of the given equations. And actually, I could use either parameter in its respective equation, and I will get the same point by virtue of the fact that they cross there. So I'm going to just take 2 and plug it into my equation for R1. So when I do that, I'll be adding the vectors negative 5, 4, negative 5, and 4, 2, 6. As my result, I get negative 1, 6, 1. So that tells me that the point of intersection was the point negative 1, 6, 1. The check step, when you're looking to see if 2 lines intersect, is incredibly important because of what it actually means if the check step fails. If the check step fails, what's going to end up happening is you'll have taken your 2 equations, you'll solve for your values of s and t, but then you'll plug it back into that third equation and something doesn't work out. You get that your left side doesn't equal your right side. What that means is that the lines do not intersect. People often wonder, how can it be possible that they don't intersect if I have solved for 2 parameters that seem to work with the equations? And it's actually a tricky thing about lines in 3 dimensions. The reason you're able to find 2 parameters that work is because the 2 lines actually come very close to each other in 2 of the 3 dimensions. So let's say I had a line that passes through the point 1, 2, 0, and another line that passes through the point 1, 2, 3. When I take those 2 equations and solve for that missing parameter, I'm going to find results that work because the x values of these points match and the y values of these points match. But when I plug the parameters into the equation I get from the z coordinates, I'm going to notice that it falls apart. The check step doesn't work because I'm going to end up with 2 values that are not equal to each other. And that actually happens because of something that's unique to lines in 3 dimensions. See, in 2 dimensions, we only ever had those 3 cases. The lines could have been directly on top of each other, which was coincident. They could have been parallel to one another, or they would have crossed. But the one thing that we're overlooking is in 3 dimensions, lines that might look like they cross from one perspective actually miss each other when viewed from a completely different perspective. And so if this was in 3 dimensions, these lines from a top-down view might look like they cross each other, but when I look at them from the side, I see that there is actually a gap between them where they don't cross. We call these lines skew lines, and that's actually the 4th possible case of how lines can interact in 3 dimensions. So lines are skew from one another when they don't intersect, but they look like they almost do. So if you were to try and solve for their point of intersection, and you actually discover that they don't match on all 3 coordinates of that point of intersection, then we know that they're skew. So essentially what you're verifying there is that only 2 out of 3 coordinates are in common for a point. So they come really close to each other, but they do not actually cross. The way we describe their existence mathematically is we say that they're not coplanar. So remember, when we draw in 2 dimensions, we're drawing on the Cartesian plane. Essentially, picture it like an infinitely large flat sheet of paper. And in order for 2 lines to be skew, what essentially has to happen is they can't actually be placed on the same sheet of paper. Here I've included a video of 2 skew lines pictured in GeoGebra, so you can see as I rotate the image around, from some perspectives, it looks like these lines might intersect, but when you look at them in 3D, you realize they do not actually pass through each other, they just pass very close to each other. So there is no point of intersection to be found here.